right. Well, welcome, one and all. Welcome to the first session of the Ottawa RASC for 2012. I think we're going to have an exciting year of stuff. There's a lot of stuff happening in astronomy. I hope you all had a great Christmas and a happy, relaxing holiday with family and friends. I see a lot of old familiar faces, old friends, a few faces I don't recognize too. Just a quick show of hands, how many new members do we have? Ah, excellent. The people visiting us for the first time, yeah? Excellent.
Good way to start there, Paul. Turn out the lights and ask for a show of hands.
I'm an astronomer. I have night vision. Yeah. Always one in the crowd, eh? Always one in the crowd. Well, I know, it's true. It's true. Well, for the new members, I tell you, your timing is wonderful. 2012 promises to be an exciting year in astronomy and space exploration. We've got the Kepler Space Telescope discovering new exoplanets almost on a daily basis. We've got the Curiosity rover, a unit about the size of a small car on its way to Mars, scheduled touchdown later this year and pry out some more of Mars's secrets, taking up where Opportunity and Spirit left off. And we have the Russian-Chinese Phobos Grunt mission that was supposed to go to Mars but didn't quite make it out of Earth's orbit. That's scheduled to re-enter sometime in the next 2 weeks and promises to spew all manner of toxic propellants and biological samples somewhere onto our planet. Hopefully it'll burn up or not land on anybody that we know. I don't know. Space exploration. And of course, as I say, your timing is great because this could well be the last year of the RASC. I know. If you believe the stuff that you read on the internet, the Earth is due to end in about 350 days. Good point. I feel better now, actually. I feel a whole lot better. You don't, eh? Well, hopefully we'll see what happens. We'll see what happens with that particular prediction. Maybe we can get somebody to give us a talk later in the year on the science or the mythology behind that. So if anybody's interested in doing that, approach myself or Chris, and we'll see if we can shed a little light on that mystery. Hopefully before December the 21st, though. You've got to do it before. Well, you've got up to the December meeting to do that. So anyway, welcome all. I'm glad you could all make it tonight. I was wondering how many we'd see because the weather forecast isn't all that great, but. Welcome back, and we have a good program lined up for tonight. We have you may remember this guy Bill Wagstaff. Yeah, he's back to haunt us, and if you don't like my style, blame him because he's the guy that put me up here. So that's the reason I'm here. Thanks, Bill. So he's going to do Ottawa skies for us. Sylvie Letourneau is going to give us our 10-minute astronomy update, and Pierre Martin's got a very interesting talk on the Selwyn fireball, which you may have heard of that re-entered the Earth's entered the Earth's atmosphere about 3 weeks ago. I'm particularly looking forward to Pierre's talk because I actually happened to see that from Canada, believe it or not. I happened to be looking at the right place at the right time. I had just gotten out of work, and about 6 degrees above the horizon to the west, I saw this thing coming down, and I went, "Holy smokes!" I thought it was a piece of space junk at first because it was a really slow trajectory, but it was very, very bright. But as I say, only about 6 or 7 degrees above the horizon. So I didn't give it much thought. And then Chris sent me a message saying, "You heard about the Selwyn fireball, didn't you?" I said, No. And I realized that's what I'd seen. So I'm really looking forward to your talk there, Pierre. Get a bit of more information on that. Then we'll do our break. We'll have some observations from members. And the one and only Simon Hanmer will give us a very interesting talk on the motions of the moon tonight. So without further ado, Bill Wagstaff, welcome back.
Thank you.
Well, gosh, thanks. Feels like I haven't been away. Anyway, going to do a very brief Ottawa skies tonight. Look as I might, I didn't find a whole terrible amount of really interesting events to talk about. So it'll be the mundane usual, what's going on with the planets, what's going on with the moon, that sort of thing. So jumping right in, next please. First off, we still have Comet Garad in the skies. Laser, there we go. Oops, I did that. Yep. Comet Garad is still in the skies. Last month it lingered pretty much in this area and didn't really move around a terrible amount, so it was pretty easy find. You know, you could go out night to night and expect to find it. So now that we're getting some clear nights here, when you do get one of those clear, cold nights, pop out with your binoculars, take a look. Over the month, it'll be progressing up this way, and eventually by February 4th, it'll be up around here. Right now, right down in this area, this being Hercules, sorry.
Did it get close to M92? That trajectory looks pretty good.
That's how we're going to see it, right? So good call there, Gary. Right, so we're down, as I said, it lingered down here. It was moving pretty slowly, but you can see it's speeding up here, moving more and more quickly. As well, you'll note that the tail turned in direction over the last little while. So it's going to stay pretty consistent over the next while, but here we are. We're just down around, just above his knee right now, and going to be moving along here by the end of the month, right up by M92. So I'll just see if I can get this. Yes, okay. As far as the planets go, Mercury right now, southeastern dawn sky for the next couple of weeks. After that, be disappearing, and there'll be a reappearance a couple of weeks later, that sort of thing. Venus, western sky at twilight. Really, there's going to be less and less over the next little while. Mind you, I find myself, there's not that much to look at for Venus anyway. As far as Mars goes, rising in late evening, it's moving towards its opposition, which will be just in a couple of months. So should be improving over the next little while. These clear nights, probably be some good observing in there. Get out and, high-powered eyepiece, see what you can do with it. As far as Jupiter goes, it's in the evening sky, setting after midnight, so still good observing for Jupiter. Saturn as well. It's rising well after midnight right now, so if you're out late, you'll be able to observe it, but earlier on, no, not so much. We're going to be able to see the same view with the rings pretty much through the entire year here. It's not going to be changing too terribly much. Uranus, currently now in Pisces, setting in late evening. A little bit of an interesting point. It's been south of the equator for quite some time now. It crossed back and forth over the equator twice last year, and it's now going to cross back over the equator to the north side on January 28th, and it'll stay there on the north side of the equator until the year 2052. So it's kind of, every once in a while you'll see that crossing happening. The position will change slightly from your point of view. And last of all, Neptune, low in the western evening sky, disappearing around the month end. Really, you might be able to pick it out. I'd really say that you're probably not at your best time of the year to be looking for Neptune. Lunar, January 1st was our first quarter. 9th will be full. And I guess the one that's most interesting to us, new moon, January 23rd, about 2 o'clock in the morning, something like that. Okay, and that's it for this time.
It's flexible. Okay, good evening, everyone, and Happy New Year to everybody. Let's see if this works. Excellent. So first tonight, I'd like to talk about the James Webb Space Telescope, because this past summer, I had announced that the U.S. House of Representatives Appropriation Committee on Commerce, Justice, and Science, they were going to cancel Jeb Webb Space because of funding. It was part of their budget cut, but that was, the funding was restored as of November 17th, and Jeb Webb Space is now being worked on again. New launch timeline is 2018. And the latest news on Jeb Webb Space was that they they did the last of the 21 mirror testing on the deep freeze test, and so they were tested and to ensure that they could withstand the extreme low temperature for the operation in space, and I think they have passed. Also, a little note from our president, Al Scott, who asked me to add that the Canadian Fine Guidance Sensors has been also in cryovac testing at the David Florida Labs in Ottawa in December and during the holidays. I don't have any results on that, though. Tonight, I'd like to spend some time on the Kepler mission. As Paul has just mentioned, it is quite interesting. The Kepler Space Observatory was launched in March 2009. Its mission to discover exoplanet, and as you probably know, it's named in honor of the 17th century German astronomer Johannes Kepler, which I added the slide here, which is part of one of our school outreach program, therefore a bit of a different format for the kids. Kepler is measuring the variation in brightness of about 150,000 stars, so the possible transits of planet candidates, with its only instrument on board, which is a photometer. Kepler will wait to see 3 transits before it goes to some ground-based observation and additional info from Spitzer Space Telescope to confirm the discoveries. Kepler is observing in the constellation of Cygnus, Lyra, and Draco. Now, up to now, Kepler has 2,326 planet candidates. There's over 200 of these that are near Earth size. 680 are what they call super Earth size, though a little bigger. Over 2,180 that are Neptune size, and over 200 that are more like Jupiter size. And there are 55 that are larger than Jupiter. But here's the thing, only under 50 of these are in or orbiting in the habitable zone. So not that many. And so far we knew of 2 small planets that were orbiting on a smaller and cooler star than our sun, and they were both on the edge of the habitable zone, more like Venus and Mars orbits. Well, so in other words, astronomers will find exoplanets all the time, but most of them, they're not in the habitable zone. And at the beginning of December, Kepler confirmed its first planet that was, or that is, in the habitable zone, and it's orbiting a sun-like star, so a star that's comparable to our sun. It's named Kepler-22b, and we don't know yet if it's, what is the composition of the planet. We don't know its mass, so we don't know if it's rocky, gas, or with a lot of liquid, oceans, or anything like that. But Kepler-22b is located 600 light years away in the constellation of Cygnus. Kepler-22, the star, like I said, is very comparable to our sun. It's a G-type star, and it's only slightly smaller and cooler than the sun. Now, the new world, though, if you can see at the bottom of the slide, is 2.4 times the radius of Earth, so quite a little bit bigger. And it orbits its sun in 290 days, very comparable to ours. So, but we don't know its orbit shape. So if the orbit is quite highly elliptical, it is possible that the planet only spent a little bit of its time within the habitable zone. We don't know if there's atmosphere, but let's say if there is no atmosphere at all on Kepler-22, the temperature on the surface would be close to about minus 11 Celsius. So like a little cool winter night. But if there is an atmosphere similar to ours, the temperature could be around 22 Celsius, which is a nice spring day for me. But there's a kicker. If its atmosphere is more like the greenhouse effects of Venus, now we're talking about an average temperature of the surface of 460 Celsius. It's a little too hot for me. Now, another discovery from Kepler, and that was done after this announcement, beginning of December. This one was more at the end of December. And they announced that they found two small planets, and there are the two smallest so far. There are Kepler 20e and 20f. Their diameters are, well, you can see compared to Mercury. Well, I have another, I can go to that slide. Very similar to Earth, so we're talking about 0.87 and 1.03 times Earth. So close to Earth and Venus, as you see here. Their system is located 1,000 light year away, and this time it's in the constellation of Lyra. But these two are too close to their star to be in the habitable zone. Their temperature is more the order of 760 and 426 Celsius. And another observation is this is the order of the planet in the system. So we're talking about these two that are comparable to Earth in size. And these other bigger ones are ordered that way. So this is the closest one to the sun, then it goes with a small one, then a big one, then a small one, then a big one. So that is very different in our solar system. And we don't know who's more predominant. Are we going to find more system like this, or are we going to find more system like our solar system, which is a bunch of small rocky planets than the big gas planet? And also you can note here that this is the scale, sort of, and they all orbit, like I said, closer to the star, not in the habitable zone, and closer than Mercury would be if Mercury's orbit was in that system like this. But nevertheless, those two planets are of similar size to Venus and Earth, and we are starting to see a smaller planet and more planets in the habitable zone, so we're getting closer to maybe finding a Earth twin. And that is it. Now, I don't have a slide, but I see I have 1 minute and a couple seconds, and I can just, as Paul has mentioned, the Mars Science Laboratory launch at the end of November, and is on the way to Mars. And supposedly there's some science happening already. I didn't have time to do research that, but maybe next month we can look at that. Lots of fun things for 2012. Thanks.
Thank you, Sylvie. Just a small appendix to Sylvie's talk, especially on the exoplanets. For those of you that may not be familiar with the concept that when Sylvie talked about the habitable zone, that is a theoretical zone around any star in which, if there is a planet that is orbiting within that zone, there exists the possibility that water can exist in liquid form on that planetary surface. It's not a guarantee, but it's just the right distance from the star given the star's temperature that makes possible the existence of liquid water on a planet. So as far as we know, and as far as life as we know it, you got to go where the water is, and that's why we're interested in any planets orbiting in the habitable zone. All right. Oh, I forgot to mention too, I hope you enjoyed that little video interlude that we had at the beginning there. I thought in case some of you hadn't seen that, and if you've ever wondered what it was like to be an astronaut on the ISS, looking back out through the porthole back at the lights of home, well, there you go. That video kind of shows it quite nicely. And there's no place quite like home. Exoplanets notwithstanding. All right, next up on deck, Pierre is going to talk about the Selwyn Fireball. Pierre?
Okay, thanks, Paul. So I will talk about the Selwyn Fireball momentarily, but first I want to talk about the meteor physics group of the University of Western Ontario and some of the really cool stuff that they do. I think you'll find that it's pretty interesting, the kind of networks that they are running. So to start, I'm sure that most of you, the vast majority in the room, you've seen a meteor at one point or another in your life, probably several of them. And a number of you have probably seen a really good sized fireball as well. Maybe one that exceeded the brightness of Venus, produced a gamut of colors, maybe fragmented spectacularly, left a persistent train, or maybe even produced a sound. Fireballs do happen, and they can be a spectacular sight. And now, fireballs are very significant for the reason that when they happen, it usually means that there's something either big or fast that's entered the atmosphere, or both. And to give you an idea of the size of the meteoroid and the velocity involved, if we look at a very slow-moving meteor, one that travels maybe 20 kilometers a second, to produce a fireball maybe the brightness of Venus, you would need a particle or a meteoroid with a mass of about 100 grams to produce something about the size or the brightness of Venus, and assuming that it's traveling relatively slowly, like I was saying. In the case of a really fast-moving meteor, one that slams into the atmosphere at 60 kilometers a second, you would need something as large. It could be as small as only 1 gram to produce a similar brightness, something as bright as Venus. And that just goes to show that the velocity of these particles when they slam into the atmosphere can be really tremendous, can produce a lot of energy. And so there is both the size of the particle and the movement in the atmosphere. Now, fireballs are also significant for the very big reason that they are a good indication that there might be something that has reached the surface of the Earth as a meteorite, especially in the case of the slow-moving fireballs, or the ones that enter the Earth's atmosphere at a relatively shallow angle. That's the kind of stuff that stands a better chance of surviving the entry of the atmosphere and perhaps eventually dropping meteorites onto the ground, onto the surface. And of course, meteorites on their own are very significant, very valuable for the very reason that they are a key to our understanding, to our knowledge of the dynamics and the history of the solar system. So very, very significant stuff. So that's why it's, the study of fireballs have taken a predominance over the past several years. Several groups or scientists around the world are setting up networks or detection networks to try and more precisely establish the position and the exact area where these fireballs occur, to better pinpoint where meteorites can also be found. So a little bit about the University of Western Ontario. This is the group that's led by Peter Brown and company. And they do some really cool, significant and cutting-edge detection work there. They obviously study in the detection and the research of small bodies in the solar system, anything from the very small meteoroids all the way up to the dynamics of the comets, how they behave and how the sun affects them, and also all the other forces. And they also happen to be running a number of fireball or bolide detection networks in southern Ontario, such as infrasonic systems, which basically it's a way to listen to meteors. Large meteors like fireballs can produce very low frequency sounds that we call infrasonic sounds. And this is due to the shock wave that's produced ahead of the fireball. And this can be detected by specialized instruments. Radar is another method to detect meteors. When a meteor slams through the atmosphere, it can leave behind a trail of ionized particles. And by bouncing radar onto this trail, we can actually detect the signature of a meteor. And the third big component that these guys are running is the all-sky video network, video camera network. And this is what I'm going to talk a little bit about in detail, because it's actually something that they're doing that's been quite successful. So move this forward. So what this is, they call it ASGARD, which stands for All Sky Guided and Automatic Real-Time Detection. So it's a network made up of 7 different stations, each containing an all-sky video camera. And each station are spaced approximately 50 to 100 kilometers apart. And what they do is the goal behind this project is to have these each of these camera continuously monitoring the night sky whenever it's clear, and record anything, any fireball or significant meteor activity that occurs. So if it captures something significant, it will compare, and it will hopefully have more than one video station record the same event. And by doing that, it will be able to correlate the data together and determine very precisely critical information about that particular fireball, such as its height, its length, and its duration, the direction of travel in the atmosphere. Those are all really important clues. And the more precise these details are, obviously the more pinpoint the better the chances of perhaps locating meteorites on the ground. So the system can do something else also, is that if there's a significant fireball, it can also automatically trigger other detection instruments within the Southern Ontario meteor network, such as the radar and the infrasonic systems that I was mentioning about earlier. So the cameras can automatically kick in those other systems to hopefully gather data or to retrieve information that these systems have detected. So a little bit about the software, or the process, how it works. Software that was designed for this, for the All Sky network, is specially designed. Of course, it's designed specifically for this purpose, running under the Linux operating system. And the whole idea is to automatically detect fireball events in real time and continuously with the minimal maintenance. The idea is also to correlate the data. So whenever there's a detection, a bright fireball, the stations will automatically gather the information onto a main server and then correlate the information together. So by getting different views from the different cameras that are spaced apart, they can actually get a really detailed and really accurate profile about the fireball in question. And once all the data is put together, then a message is automatically emailed to the team members, telling them about all the detections that occurred, or all the fireballs that happened, and basically alerting them that there is something that significant that happened. As far as the hardware, the cameras themselves are high-cam with the Sony EX-View HAD CCD, and they're each running with a 1.6 to 3.4 millimeter f1.4 lens. The enclosure itself, it's basically a clear acrylic dome, and inside the enclosure there's even a thermostat to produce a little bit of a heat, as well as a fan to circulate the air and also to prevent dewing on the glass dome and the camera lens. On top of that, they have each of the camera has a photo sensor that's designed to automatically shut off the camera when it detects enough daylight. So in the daytime, the system is off and will kick in again at sunset. And apparently the domes have to be replaced every few months because of dirt or debris. Eventually they'll become dirty or fogged up enough that they'll need a replacement. The videos are running at 30 frames a second. And the cool thing also is whenever there's a detection, the cameras will automatically log the time, and will do so by GPS. And this is also calibrated constantly, so the timing is extremely accurate. And they use also something that's called the network time protocol software to be able to get the timings all very precisely calculated. So when there's a detection, there's three things that happen. The first thing is what's called a quick review graph, and this is in 4 parts. So on the graph, it will show a fireball, roughly the rough position in the sky of the fireball. It will demonstrate the second graph with the length of time that it took for the event to happen from start to finish. And naturally, a good indicator is most meteors, even the brightest one, will typically last no more than a few seconds. And if an event lasted many, many seconds, then perhaps it's not a fireball, but it might be a satellite or debris, space junk reentry, or it could be something else. Could be just an aircraft going into the field of view if it's going by for several minutes, or a bright satellite or something of the sort. So this can right away give a good hint as to the origin. On the bottom left part, it'll show a map with a rough map of the Ontario, but the meteor plotted on top of the area where it happened. And finally, it'll show, or it'll give a preliminary orbit of the meteor or the fireball. And all this is available quickly for a quick review the next day after it happens. Now, the main server will also do a lot of things. Like it'll figure things out, it'll match things together, and it'll combine the data, as I was saying earlier, to really give a really precise, or hopefully as precise as possible, visual on the fireball. Lastly, the last thing is the system will then go back to the cameras and actually request the raw data to be able to be further studied later on. And this chart just gives you the idea of the sensitivity of the system. It's the magnitude distributions of a number of detections within a given period of time. Not every one of them, but I think it's over the span of a few years. And as you can see, the ones that are most frequently seen are meteors of magnitude -4 or -5, so slightly brighter than Venus. And as we go to the brighter and brighter fireballs, obviously they are very few. They become definitely a rarity. And on the other end of the scale, you notice how it rapidly goes down at about magnitude -1, and that's simply the cutoff, or close to the cutoff of the camera sensitivity. So even though in reality we get many, many more of the dimmer meteors, the cameras are not designed to be able to capture them. So in all, since 2006, there's been approximately 2,000 fireball detections by the network. Now on this graph, it shows you so far a number of the possible meteorite dropping events that occurred. And the red arrows are the paths, represent the paths of the fireballs through the atmosphere. And the blue circles, the blue ovals that you see, are the projected areas where meteorites might have been dropped by these fireballs. So none of these that you see have been recovered so far. So there's a good chance there could be meteorites lying in any of these areas. And you notice how occasionally the distance between the endpoint of the fireball and the possible meteorite area can vary from one to another. This always depends on the number of things, like the angle of the fireball, how deep it penetrated the atmosphere, perhaps how large the particle might have been, and other factors like the wind speed that could have pushed these particles. Now, even the largest of fireballs will typically completely burn out maybe about 30 kilometers in altitude. And this is really low for meteor standards, but at that point, what happens once the fireball extinguishes, if there's anything that survived the entry, there's what's called the dark flight. And that phase is essentially where the velocity of the meteor ceases, and it's the Earth's gravity that takes over any particles that survived and just drags them down in dark flight, so there's no more light being produced, and the particles just eventually will fall to the surface by gravity. And that's what we call the dark flight phase. So now I'm going to talk about the Selwyn fireball that Paul mentioned to you a bit earlier. So this was on December 12th, just after 6 o'clock. There was what was estimated to be a basketball-sized object that was that entered the atmosphere and was captured by the all-sky camera network. The fireball entered above Peterborough, and it was, and even though it passed over Peterborough, it was still seen very widely by the public. And as Paul mentioned, it was seen as far as Canada. The angle of entry for this meteor was very shallow, only about 25 degrees against the atmosphere. And it was a really slow-moving one, a really slow poke as far as meteor standards. This one was measured by the camera network to be only 14 kilometers a second. So that's almost as slow as meteors can go, just barely faster than maybe a fast-moving satellite. And the date, the timing of December 12th, even though it's close, relatively close to the Geminid meteor shower, it was ruled out as a member of that shower. It's just a coincidence. So what I'm going to show you is the video captures. So on the next, what you see here is the a still image that was captured by combining all the still frames together to show you the path. But I'm going to show you some of the videos of that fireball. Some are not too, look at the very top of the screen, and there it is. So for this camera, it's actually quite far away. And some of them you'll see it a little bit better. This is one of the better captures right here. And unfortunately, none of those were seen right overhead. There's camera number 3 on the right side. As you can see, it's really slow and persistent. And that's usually an encouraging sign for possible meteorites when something like that happens. At the very top, just barely. And it's gone. And bottom left corner. Another pretty good capture here. You see almost the entire path. So as you can see, very slow, very long lasting. And of course, seeing it on video does not do justice compared to seeing it for real with your eyes, where the camera is not designed to capture a pretty picture or capture the colors or the subtleties that a human eye can see when those events happen. So, but what it does very good is measuring the exact position and the exact details of these events. So we're looking now at the track of this of the Selwyn fireball as it began over Lake Erie and passed over almost directly over Peterborough and finished a bit north of it. And it's very likely that this meteor has dropped some meteorites somewhere east of Selwyn or close to Upper Stony Lake. And there could be as many as a few kilograms of meteorites on the ground waiting to be found. And there's a closer view. As you can see, the end point of the meteor here, at roughly 31 kilometers altitude. And any meteorites might most likely be found within the square area. And I did have a look in Google Maps, and first thing that comes up is a lot of trees, lots of water. And that brings me to say that locating meteorites is a huge, huge challenge, very difficult. And that's essentially the big reason is our local geography and our weather. Anything from forests, lakes, snow can easily hide or camouflage any surviving fragments. Or it could be simple cases of fragments being located on private property and maybe never to be recognized or recovered. Now, this is one of the reasons why the University of Western Ontario, the physics group, they do a pretty good job of alerting the media and letting people know that if there's anything unusual, if you find things like black rocks or rocks that are heavier than usual, perhaps magnetic, if you see things that are odd in your backyard, like dust being kicked up or maybe a broken window, that can be maybe a hint that there is something unusual that happened and to keep an eye out. Now, of course, any find can be extremely significant, very valuable. And even better is a fully documented fireball. That is a fireball that's been seen, recorded, all the way to recovery of actually finding pieces of that event. That has not happened often. There has only been about a dozen cases like that has happened in all of history. So it's very, very infrequent. It's one of those things that it's almost the equivalent of a NASA a planetary return sample mission. That's how significant an event like this is, from seeing a fireball all the way to the actual recovery. That being said, the University of Western Ontario has the have been very, very fortunate to have been one of these cases, one of these very rare cases where there has been a major fireball and they have recovered pieces. And I would like to talk a little bit about that. That brings us to the famous Grimsby fireball of 2009 in September, and a little bit of the story behind that event. Now, the Selwyn fireball that I talk about, that was no small thing. It was a pretty big fireball, maybe around magnitude -8, roughly similar to the brightness of a quarter moon or so. So those do not happen often, and they are very spectacular, as I'm sure Paul will tell you. Now, this fireball that occurred in 2009, this was a magnitude -18 fireball. And you've heard me correctly. -18, or roughly 100 times brighter than a full moon. So very significant. So we're talking about a bolide that entered the atmosphere in southwest Ontario, had 3 major bursts along its paths, and sonic booms for people who were located directly below it. So this was a big, big thing, and really, it was well seen by many, many people. Again, a fairly early evening fireball, and fortunately, the all-sky camera network of the university captured this very, very well. And I would like to share a few of these videos with you. There's the first one. I imagine seeing that with your eyes. Number 2. A little closer to the horizon, but notice how the sky just totally lights up, like almost like daylight. Here's camera number 3, going in the bottom.
Those are clouds, Pierre?
This is those are clouds. Yes, that's right.
You brought up a good point too. There's no sound with these cameras. They don't record sound.
No, I don't believe they're designed to record sound either. And just as a reference, you're looking at the moon on the bottom right. You see how massive this meteor is. And
Would sound be viable? Like, could you actually hear a sonic boom from one of those if you were at that station?
oh, I would assume the very first video that you saw, where it was almost overhead,
Yeah.
there was most definitely a sonic boom, as was reported by a lot of people who were located
Like, who
underneath.
recorded it?
No, I don't think there was any sound recorded, only witness reports for that. And it sounded, it was a form of a very distant rumbling thunder. That's what was reported. So as you can see, very significant event, and this was classified as being an Apollo-type object that entered the Earth's atmosphere at roughly 21 kilometers per second. And from this event, it was presumed that several kilograms of fragments fell down to the surface just to the west and south of Grimsby. So the endpoint of the fireball was only 19 kilometers, which is very low for a meteor. And that got these guys at the meteor physics group very excited, because they knew for sure there had to be a lot of fragments on the ground from this event. So a search was undertaken right away in the projected strewn field, the circled area right here. And it took only a few days, well, not even a few days. I think the next day, somebody right away found something unusual. It was the first piece that was recovered. And what happened is a guy went to his SUV and found that his windshield was broken. It was shattered. And he found pieces of rock inside his car and figured, oh, well, somebody vandalized my car. So this, the first recovery was actually unrecognized for several days until the person in question found by the news or the media that the meteor physics group were really after the public to try to get information or anything unusual like that, and that's how it was finally recognized. And a search was taken, and this was followed by as many as 13 additional meteorites that were located within an area measuring roughly 4 by 8 kilometers. So these, many of these fragments were actually complete pieces. Like a lot of times after they hit the ground, they might break up, they might split in half. But several chunks were intact, and this was also really good news for the team, where they could use these chunks for further study and to test their computer modeling software for the dark flight modeling. That is how well a computer calculates the endpoint of the fireball and the free flight of the particles down to the surface. So a lot of information could obviously be gathered by these very fortunate finds. Now on the next one, there's one of the fragments. And on this video, which should be loading up, that will show you the orbit of the small body, all the way to the impact point on the Earth. And you see the position of all the cameras. And this is roughly where it entered the atmosphere. So this it's pretty cool stuff what they're able to do with simple all-sky coverage.
Pierre,
Sure, go ahead.
you mentioned the size of the footprint was about 4 kilometers by 8 kilometers. How would they search an area like that? Like, how many people would have been out combing that area? That's a big chunk of land.
Oh, absolutely. And to be honest, I believe there was only about a dozen people searching, and that they were able to find all these pieces. And that just goes to show you that there is absolutely many more fragments that are waiting to be found.
Probably still there.
They've only located a tiny fraction of what's probably out on the ground. Absolutely. So now, next video I'm going to show you is another kind of fireball that was captured by the All-Sky Network. And fireballs are actually not all created equal in the sense that not every fireball will produce meteorites. The ones that will never produce meteorites are the really swift-moving ones, the ones that enter the atmosphere very steeply, or any one of the cometary fireballs, the ones that we see typically during the meteor showers. Those are definitely too brittle and too not enough mass or not solid enough to penetrate anywhere deep in the atmosphere. So there's the example. You'll see it's a beautiful fireball, actually. Next one. There we go. So very brief, bright. It lit up the sky. That's the kind of a typical fireball. You can maybe play it again in case we missed it. The kind of event that people would typically see during the Perseids shower. And these were completely vaporized very high up in the atmosphere. So there's a lot of these kind of captures that the cameras will find, and these will very quickly be dismissed as being a non-meteorite producing event. Now there's the other interesting factor is the two fireballs, the Selwyn and the Grimsby fireballs that I showed you. Both of these events were relatively early in the evening. And I'm sure you've often heard that we typically see the most numerous meteors after midnight in the early pre-dawn hours. And that's actually very true. However, what happens in the early morning is the Earth's turning into the area that we're also traveling in our orbit. So yes, we're picking up more material, we're seeing more meteors, but a lot of this stuff is also plunging more deeply, more steeply into the atmosphere, and more swiftly as well. So any material by those hours would more than likely be vaporized or be completely burned out high in the atmosphere. And this goes even for the more solid particles, versus the ones that, the less frequent ones that will happen in the early evening, where they are catching up with the Earth's rotation by the way they're entering the atmosphere. And they stand a better chance of actually surviving the flight in the atmosphere and producing meteorites because of the shallower angles and the more gentle entry into the atmosphere. So it is actually a fact that there are more meteorite-producing fireballs in the evening hours than there are in the morning, interestingly enough. Now, like all machines, there can be false alarms, there can be errors or misdetections. And this is certainly the case with the Southern Ontario Meteor Network. And the few videos I'm going to show you will show you just the kind of stuff that they tend to detect on a pretty regular basis. They call this one a dark and stormy night. Blowing in the wind.
Was that?
I think it was a piece of snow, or ice, but I'm not sure. And you notice how whenever there's a detection, there's also a crosshair, and this basically is what triggers the system, the software. Creepy crawler. I thought they said this would be easy. Just passing through. Pit stop. And they've captured also a sprite. This is a high atmosphere. You'll have to play it a few times, yeah.
Right here.
You'll see a flash, very, very brief. And just before the flash, you see a very dim glow over the horizon, like a very dim flash before you see the sprite. This is actually a thunderstorm below the horizon, and the sprite is the actual electrical discharge being sent up way, way high in the upper atmosphere, where there used to be debate on whether these things actually existed, and they've been proven to be the actual case.
They found it on the ISS. They photographed them for the first time with the ISS.
They did? Okay.
With the HD camera, yeah.
Okay, great. And of course, with this network being active for so many hours and for so long during the year, they stand a good chance of finding a lot of these events that normally would not be seen. And that pretty much concludes my talk.
You got one more.
Oh, one more? Oh, forgot about this. Anyone care to guess what this might be? So I'll leave it at that. Thank you. Oh. Question?
I noticed the strewn field for the Grimsby, the ellipse was end-on to the direction of the fall.
Yes.
The meteor was traveling. In the earlier one where you show in the map where you show all these the trajectories, and the strewn fields, apparent strewn fields, seem to be at something of an angle, quite an acute angle to the direction of the travel. Why weren't the ellipses sort of end-on to the...
It's a good question. I think what can very often happen with fireballs is if they detect a lot of fragmentation over the course of the path, that means there could be meteorites that start to fall, go into free flight, even well before the termination point of the fireball. So this will naturally have an effect on the angle or the area where they will fall, and can cause the ellipse or the strewn field to be shifted or to be on a different angle than other fireballs, which might have a very gradual or a very, say the more gradual burnout, where the terminal area is where most of the meteorites or potential meteorites would fall, and this would cause the end point or the ellipse to be situated closer to the end point of the meteor.
Like on that one on the slide right now, that just seems a bit counterintuitive.
Yes, it seems like it, and I was quite curious when I saw it at first, and I think maybe one of the big things they look at is the wind speed also. So they figured that most of the breakup probably occurred at the end point of the meteor around here, and the fragments just kept going into free fall and being pushed slightly to the right by the wind.
That's what you call the dark flight?
The dark flight path, that's right. So the end point, the fireball itself stopped being visible at this point, at 31 kilometers high, and any surviving fragments would just be going into free fall right up until they touch down on the ground.
Here,
Sure.
University of Western Ontario has this network. Are there any other networks like this in Canada? You're into meteors, or
Yes,
anything
yes.
like this in Quebec or British Columbia or something?
Yes, there's one in British Columbia, and there's 3 or 4 of these networks in the United States, and a number of them around the world. And they are increasing in frequency. Go ahead.
Yeah, Pierre, with your random paths, I didn't see any coming directly from the east. Do you have any explanation for that?
Yeah, good question. If we look at the different paths,
Yes.
yeah, I would presume that probably has a lot to do with the Earth's rotation and the movement of the planet in our orbit, where anything coming, there certainly are fireballs coming out of the east, but these would probably be more typically the ones that are coming up against our movement of rotation and would be the really swift guys. The ones that are most likely plunging deep in the atmosphere and blowing up like a snowball that you threw on a brick wall, completely disintegrating. While the ones coming out from the west, maybe more or less west, maybe a bit south or north or northwest, would be the slower guys. That probably have the better chance of surviving. So yeah, it's a good point.
Pierre, I don't know if it's just coincidence or not, but if you actually look at those final fall areas, 2 of them fall into Lake Huron, and all of the others are on the shores of the Great Lakes. Is there an explanation for that, or is that just the way the chips have fallen?
The way I see it, I think it's just pure dumb luck. It's just the way, or no luck because it's over water. And I think the nature is, with our planet being surrounded mostly by water, the nature is that most of the big fireballs are never to be recovered, and which is just adds to the difficulty in it. But no, it's true. We have 3 events right onto the open water, Lake Huron, and relatively few over landmass. But I think it's just the luck of the game. Go ahead.
Just wondering, we're seeing a lot coming from the south, could be a sign of something bigger to come? Prelude of something bigger?
I'm sorry, what's that?
No, with these smaller pieces
Mhm.
coming always from the same direction,
Oh, yes.
could be before something larger.
It is 2012, Gary.
Yeah. Yeah, who knows? Eh?
Just a bit of trivia
Sure.
information, where the 6 is where the Can-Am meteorite crater is,
Oh,
right
yes.
in the bottom of Lake Huron there.
True enough. Eh? Yeah. Thanks for sharing that.
Pierre, does the government still pay people for recovery of fragments? I've heard that before, that they will actually buy specimens. Is that true?
I think in some cases they still do, yes.
Yeah.
If especially if they recognize that there's a very unusual composition or a meteorite specimen that would be valuable for science, I would think they would probably want to buy or find any means possible to get the pieces. And I know for sure the physics group of the university are always eager to get their hands on those items. And certainly it's recognized that any meteorites falling onto private property belongs to the person who owns the land. There's no ifs or buts about that. And the university will often tell people, we'll borrow the piece for a while and we promise we'll give it back, but it's valuable enough that we would like to be able to study it.
The Royal Ontario Museum buys them.
Mm-hmm.
They bought some pieces.
And building a good collection, I'm sure. That's it. Thank you.
All right. Our next segment, observation reports, images and observations by members. Our first, always our first gentleman, Mr. Commission. What have you got for us, Paul?
Good. This is 188. This particular cluster, open cluster, is the closest to the celestial pole. It's at approximately 85 degrees north. So everybody's looking at Orion and the Taurus and all this kind of stuff. Turn your scope the other way, go up from Cassiopeia, you'll find this. This, by the way, is one of the oldest known open clusters that there are. So it's an interesting object. It's not too bright now, mind you. It's about 8.6. So that means you would probably have to have a 4-inch telescope to see it. But if it's a good, clean, clear night, you can probably see it with a large set of binoculars.
Are most of these stars members of that cluster, Paul?
Yeah, they are. This pretty well takes the cluster in the picture there. The heart of it is right there, just to the left of the center there. That has to be. The other ones are also members of the cluster. The cluster's fairly large. This picture is about 15 by 12 or 10. So the cluster is about 13 minutes in diameter. Approximately 13 minutes in diameter. Next one, please. Oh, this is the owl cluster in the Cassiopeia. This is a very interesting cluster. There's the two stars at the bottom that people claim to be the eyes of the owl. Now, there's certain debate here as to whether they are part of the cluster or not. Now, Scott, the famous observer, says that they are, but many people claim that these two, the two bright ones down there at the bottom, are not members of the cluster. I don't know. This thing is about 7,900 light years away. And this is quite fairly bright. This you can see in perhaps in a 10 by 50 binocular. You could see them. This particular one, it's bright enough, and it's an interesting one. A lot of people observe this particular one. Okay, thanks.
Thank you, Paul. And next up is Gordon Webster.
Well, Happy New Year, everyone.
The first one here is Jupiter with 5 moons. This is December 17th around 9 o'clock local time. And where's the pointer gone? There it is.
You know that's an extra moon.
Sorry?
You know that that's an extra moon.
Yes, right there.
Yeah, it's Phobos.
Yeah. It's actually star SAO 92690, which is near Europa. Next, please. Next one was a shadow transit right here, shadow of Europa, right beside the Great Red Spot. And that was on December 20th, again, or just after 9 o'clock. Next, please. M77, okay. M77 is just small and bright with a fairly bright stellar core, and it's probably a reverted imagination, but I was pretty sure I saw spiral arms on it. And that was my last session with my old 8-inch telescope, which I miss. But I have a new 12-inch, which I love.
Merry Christmas.
Okay, yes, indeed. Next, please. And this is with the 12-inch. This is NGC 1501, which is the open planetary nebula in Camelopardalis, or whatever it is. Yeah, couldn't see the 14 meg central star, but doesn't show really well. But there's a dark center to the cluster and a little bit of, or to the nebula, and a little bit of modeling in the halo. And that, as I say, that was with the 12-inch. And next we have Trumpler 1, which Paul showed quite recently, either last month or the month before. Open cluster in Cassiopeia. It's about magnitude 8.9. And I think that's it. Yep.
Is this with tracking or no tracking?
Tracking. It's delightful.
Your shadow transit there,
Yeah.
it was right next to the Great Red Spot. A number of years ago, I made a sketch of a shadow transit, and the shadow was sitting right in the red spot. It looked like a big eyeball with a
Yeah.
pupil.
Yeah, it was really neat.
What eyepiece were you using?
We live for those moments, and I don't know why.
That was an 8. It's an 8 mil eyepiece on a 1500 scope, so it's about 187. Any other questions?
What scope do you have now? What's the new one?
It's Skywatcher collapsible Dob, fully go-to. Which, yes.
How long does it take you to sketch like
I cheat when I do Jupiter. I'll draw a very rough circle because they're hard to draw, and then just the dots for the moon. And then later I'll put in, I'll sometimes put in the bands that I can see. But this one was done later. I enlarged, I've scanned the sketch, enlarged it, printed it out, with just a circle for the planet, and then used colored pencil to put in the bands, scanned that back in, cut it out, and pasted it into the inverted one with the moons on it.
Isn't photography a lot easier?
It's not as much fun. This is labor intensive after the fact as the photography is, but it's nowhere near as intensive as the photography is at the eyepiece. This is fun at the eyepiece.
It's very unique.
Thank you.
But you're seeing more bands than I see often.
Yeah, I was that was a really good night. And Stellarium, it's probably the way I've set it up, but it's out of phase on Jupiter, and I never get a correct reading on where the shadow is or where the Great Red Spot is. So I'm constantly checking about half a dozen sources just to be sure I'm actually seeing what I'm really seeing. So, okay, thank you.
And our last observations come from Paul Cloninger. Why, thank you, Paul. Thank you. All right. I got a few for you here. I'm going to motor on because actually time is ticking. So 3 nights ago, I was out from about midnight till about 4 in the morning looking for the Quadrantides meteors. And I know there's a few other lunatics in the crowd that have done likewise. Can I have a show of hands? I can see you. I have night vision because I'm an astronomer. Yeah, I know you guys are crazy. Anybody else? No? You missed a great one. Minus 23 degrees. It was wonderful. And they were just raining down like not. But I was out for 4 hours. Only saw about a dozen and a half. I think Pierre and Ivan saw a few more than that. I did manage to get an image, though. Spectacular image. Whoops, sorry. Where's my laser? Center button. There it is. Can you see that? Fabulous, eh?
That was a boy.
It blinded me, I tell you. I couldn't see anything for the rest. Anyway, yeah, only saw about a dozen and a half, as I say. There was a lot of thin cloud, sometimes not so thin, as well as a moon up until about 3:20 in the morning. So I'm sure it cut a lot of them. I think the folks out in the East End had a little bit more luck than I did, but yeah, it was worth it. Minus 23. My finger is still numb. Anyway. Next one, Running Man Nebula. This one I shot with the Malin cam. Simple exposure actually, just with a Malin cam on a small 4.5-inch f4.4 reflector there. Malin cam Junior is only capable of about 4-second long integrated exposures, and this is a stack of 81 of those exposures. So I think about 346 seconds, just under 6 minutes of total exposure time on that. Running Man Nebula is a reflection nebula just about a half degree north of the main Orion Nebula. Next one, please. Sirius. While I was in the neighborhood, I bagged Sirius as well. Sirius is beautiful through a telescope visually as well as quite impressive photographically. Brightest star in the sky anywhere on Earth, and is actually the closest star after our sun visible to northern hemisphere observers. So. 8.6 light years away and apparent magnitude of minus 1.46. Beautiful object to look at.
How close would Sirius B there?
Where would that be? That would be probably somewhere right around there. Maybe a little bit closer. Yeah. No Sirius B there for me. Sorry. This one is IC 1396. This was taken with an Orion SSP V2 CCD camera on an 80 millimeter Apo refractor. It's a stack of 4 15-minute long images, so a combined exposure time of about 1 hour. This is the one that I shot when we were out there at the Burnt Lands there, Ivan. You can see it contains the elephant trunk. It's in the constellation Cepheus. It contains the elephant trunk. This is a region of ionized gas, and it's all being sort of charged up by this central, very, very bright star at the center, which basically lights the whole thing up, except for the dark globules. They're dark enough to protect themselves from the UV being emitted by that star.
Those are a few Bernard numbers in there.
There are.
Quite a few in there.
Yeah, there's quite a few in there. Yeah, an interesting object to look at. I've been doing some narrowband work on that too, and I'm still trying to get some good close-up narrowband with one of my larger scopes I want to practice Deborah's technique there that I read about to see what I can do with that. So stay tuned, Deborah. I'll see if I can do your technique justice. Last sequence I have for you. This is just a quick thing I wanted to show you in terms of what you can see with your eye and what you can see with a camera. Our old friend Orion here, of course. This is what you might see on a moonless night out in the country where you've got a really nice sky. You can certainly see fairly deep with that. Also, what the type of image that you'll get if you take a DSLR and put it on a tripod, 50 millimeter lens. All these next images here are all 50 millimeter lenses. 8 seconds exposure time, so not very deep, not very long. ISO 800, kind of stuff that you can get for yourself though, especially now that Orion is up nice and high and it's not too late in the evening. But you can see the most prominent stars in Orion, certainly the Belt and the Sword, and you can start to see hints of the Orion Nebula. So I'm going to flip them over on the other side just to make use of the screen real estate a little bit more. That is the same image, obviously. If you if you then take the same type of camera and you put it on a tracking mount and let it go for a lot longer, you get this next shot. This shows you obviously a lot more detail on some of the objects that you cannot see with your naked eye. Some of these objects are really only visible. Certainly Barnard's Loop is a challenge through a telescope. But certainly the Orion Nebula here and the region around the Horsehead and the Flame Nebula are visible under ideal conditions. Certainly these guys under ideal conditions under a dark sky. The Orion Nebula you can see pretty much anywhere with a small scope. And the last one I have is if you take that camera and just look at hydrogen alpha, that's what you get. So you can see the region is quite extensive. There's a lot of stuff up there that's just our eyes are just not sensitive enough to register that, but the camera will pick it up. That's again just a 50 millimeter lens tracking on a telescope, combined exposure of about 42 minutes at f1.8, I believe it was.
That's quite an impressive alien face on it.
You know, I was going to mention that because we talked about there's actually two faces. That was going to be, you took my fire there, Brian, but that's okay. But can you see there's two faces in this? And for those of you that didn't was it the last meeting or the meeting before where we talked about faces? I know Brian was always seeing things on the moon. Okay, Brian. I didn't say that. But anyway, there's faces here. Obviously, you can see the face here. Can you see the other one? How about that's the nose and those are the eyes? He's an old man with long hair. Kind of looks like me, but like with hair. Okay, I tried. It's a leap. But yeah, that's so. With hydrogen alpha, it's a really interesting mode of imaging. This is with again with just a DSLR, but it has been modified to replace the stock filter with one that allows much more of the hydrogen alpha to come through. So, and again.
The Barnard's Loop is visible. You can see that in the scope with an H-beta filter.
Yes, you can. Yeah, under good conditions. Yeah.
What was that exposure, Paul?
This is actually a mosaic of two images because of the field. I didn't want to take things off to the side too much. So each side is about 21 minutes. It's a stack of 7 3-minute exposures. And then I just mosaic them together. And you can see the Orion Nebula is quite bright with this, and the region of the Horsehead is fairly pronounced too. And that's it. Why, thanks, Paul. Great meteor image. Okay, last but not least, Simon is going to give us a talk on the motions of the moon. Simon.
I get to say thanks, Paul, but I don't have a tie.
Gary made me wear it.
I know. Okay. Title of this talk, Motions of the Moon, Why the Moon is Where It Is When We Observe It. Well, if you flip that round as a question, why is the moon where it is when we observe it? You might think this should be the simplest question any amateur astronomer could possibly ask him or herself. Well, it turns out not to be quite the case, as you'll see. I'm going to be giving you a slightly longer talk than usual this evening. It requires it. Now, just for those of you that don't know, I've been giving a series of talks over the last wee while about things in the solar system, in particular to celebrate NASA's very best kept secret, which is that NASA has declared that we're in the middle, by the way, of the year of the solar system. The only problem is they seem to have forgotten to tell anybody about it, because most people aren't aware of this. But if you Google NASA and year of the solar system, you'll actually see their official announcement. So this is one of the talks in that series of talks to celebrate here at the RASC in Ottawa the year of the solar system. Maybe we should tell NASA we're doing it. They might be very pleased. As an amateur astronomer with a geological background, I really enjoy observing the moon through a telescope, especially from my light-polluted urban backyard when I can find the time. Trouble is, the moon isn't always where I expect it to be between these all-too-rare observing opportunities. Sometimes it's way above my neighbor's roofs, while at other times it's so low in the sky I have to walk upstairs to the top floor and peek out through a window to see where the hell the moon is behind my neighbor's houses. So I decided it was high time that I educated myself in the comings and goings of our nearest and most observable neighbor, Remember, it's the only celestial body whose geography and geology can be revealed by even a modest amateur telescope. So the obvious place to start was the RASC Observer's Handbook. And in fact, I started putting this together about 2 years ago. So I was looking at the 2010 handbook. This is a great resource for amateur astronomy in general, but it has a section on the moon and its orbital behavior. And here's the big but. I found it very difficult to follow because it lacks illustrations and it skips a lot of the essential background information that I needed in order to make sense of that rather dense text. Well, I looked at it again in the 2011 version and in the 2012, and it's just as difficult to follow. By chance, I happened across an article by Jean Meus. He's a Belgian mathematician and specialist in orbital calculation. And I found this article in a back issue of the French magazine Astronomie. Finally, I thought, enough illustrations that I could start to understand the complexities of our nearest neighbor's antics in the sky. And as I say, I began to understand. I'm sure there are still aspects of the lunar orbit around the Earth that escape me, just as I'm sure that there are some among this audience here tonight who understand lunar orbital mechanics far better than I do. But having decided to put together a set of simple illustrations to see how well I could explain the moon's orbital behavior to myself, I thought I'd perhaps turn it into a talk to share with you tonight. Now, I warn you, it's a complicated story. So in order to get the point across, what I'm going to do, I've opted to tell the story stepwise. And I'm going to introduce concepts in an overly simplistic fashion initially. And then I'm going to subsequently layer on the complications that reflect the reality of orbital mechanics. Now, I have to tell you, of all the talks that I've given here at the RASC on this platform, this was the most difficult one that I had to put together. And I still can't be absolutely sure that I haven't made some mistakes. So let's see how well I did. Slide, please, Chris. So first, I've got to talk to you about a problem of scale. Here's the true size and scale of the Earth and the Moon, and the distance separating them. If I were to use true scale in the illustrations I'm going to show you, you wouldn't be able to make out head or tail. So my graphics are truly Mickey Mouse sketches, but I think they get the message across. Chris? So let's start with a very simple Earth-centric geometry as a reference frame. The Earth spins on its axis like a child spinning top, and thereby defines the equatorial plane as shown here with the green horizontal line. Next one, please, Chris. Now let's add the Moon and its orbital plane so that we now are looking at the Earth-Moon system. Now remember that the Moon rotates on its own axis in the time it takes to orbit the Earth, so we're always looking at the same face of the Moon from an Earth-centric point of view. Now this is nothing special. Most moons do the same thing for reasons I won't get into here. However, for a quite different reason, the Earth-Moon system is remarkable. Of the large moons in our solar system, only the Earth's moon and Neptune's moon, Triton, do not orbit in the equatorial plane of their host planet. Although Sirius's Iapetus shows the same behavior and is larger than your average small moon, it's still not in the same size class as Earth's moon and as Triton. Now, even Uranus, with its axis of rotation lying almost within the ecliptic plane of the solar system, the plane that approximately contains the orbits of all the planets, and hence, therefore, its equatorial plane, that's to say Uranus's equatorial plane, is nearly perpendicular to that ecliptic, it's still surrounded by moons that orbit the planet within the planet's equatorial plane. Triton's weird in any event, because it orbits backwards around Neptune, which is why most astronomers assume that Triton was actually a wandering rogue body that was captured by Neptune sometime in the early part of the solar system's history. Which leaves our moon. And remember, our moon, its orbital plane sits at approximately 28 degrees to the Earth's equatorial plane. And our moon formed from the collision of a Mars-sized body with our own home planet. So as I said, this leaves the moon looking pretty well unique in terms of its orbital behavior, at least in its size class and within our solar system. Next one, please, Chris. So if now you add the solar system's ecliptic plane to the Earth-Moon system, we now have a further complication. The Earth's spin axis is itself tilted at about 23 degrees to the ecliptic plane, which then means that the moon, while orbiting close to the ecliptic, makes an angle of approximately 5 degrees to the plane in which the rest of the solar system is trying to orbit and rotate. And I think it's this angular difference between both the ecliptic and the equatorial plane of the Earth. The moon's in sort of a hybrid position. I think it's this that gives rise to many of the complications we're going to actually examine here. Next one, please, Chris. So here I've represented the orbital plane of the moon as a red ellipse, tilted with respect to our point of view. And to keep things simple, the solar system's ecliptic and the Earth's equatorial planes are represented as simple traces or lines. Hit go again, Chris. There we go. I think you can clearly see here that depending on where the moon is on its orbital merry-go-round around the Earth, hit it twice, Chris. It will sometimes be above the ecliptic and or the equatorial planes, and sometimes it'll be below them. Hit it again twice, Chris. There we go. Because the Earth spins on its axis much faster than the moon orbits around the Earth, this height in the sky determination is not a function of the time of day. It's clearly a function of the time of the month. Next one, please. So if we now introduce the sun into the picture, we can start to predict which phases of the moon within a given month will ride high in the sky and which will ride low. In this particular example, looking at the Earth-Moon system from space, the full moon, as seen from Earth's northern hemisphere, that'll be the full moon right there, okay, because the sun's over right there. The full moon, as seen from Earth's northern hemisphere, will ride above the equatorial plane and therefore moderately high in the sky, just about above my neighbor's rooftops. While 2 weeks later, the new moon, over here, will sit below the horizon. Now, in between this phase here, in between the half-illuminated moon as seen from the Earth, is the phase that will ride highest in the sky for northern astronomers, and I will easily see it from my backyard way above my neighbor's houses. Next one, please, Chris. But there's a further complication. The Earth orbits the sun and takes the moon with it. Therefore, approximately 6 months later, when the Earth-Moon system is on the other side of the sun's over here now, the height in the sky of the different phases of the moon observed by northern astronomers is reversed. Let's just flip back, Chris, and flip forward again. You can see how it's reversing depending on where the sun is with respect to the Earth-Moon system. Okay, let's go to the next one. Now, the iconic Atlas of the Moon by Ruckel contains a diagram that shows how the height in the sky of the different phases of the moon varies through a given year. This is important. It's a given year. It's not every year that his diagram will be predictive. And this is a function of the orbit of the Earth-Moon system around the sun. Now, I've tried to reproduce it here. I'll show you, not this blank. I'll show you what's actually filling in the blank. But PowerPoint drawing tools are pretty limiting. So the straight curves that I'm going to show you here should really be curved curves, but you'll get the point. So hit it. There we go, Chris. So here's what the new moon does. And you can see that the new moon in this particular year, in the winter and at the end of the autumn, is pretty low in the sky. And around about the spring-summer transition, it's pretty high. Next one, please. Whereas the full moon, as you'd expect, is doing the reverse. It's riding pretty low in the sky in the spring-summer transition, and in the winter, it's riding pretty high. Let's go for the next one. This yellow line here is actually tracking out the moon's third quarter. There we go, coming down like this and up. And so you can see that in the spring it's riding low, and in the autumn it's riding high. And if we go one more, and here in the red line we have the first quarter. There's the first quarter. It's doing the reverse. It's high in the spring, and it's low in the summer-autumn transition. So I think you get the point here. Next one, please, Chris. Because the moon's orbit is an ellipse and not a circle, the separation of the moon from the Earth varies over the course of a lunar cycle. In other words, a month. Between closest approach, which is perigee, and the greatest separation, which is called apogee. Next one, please, Chris. So this means that the apparent size of the moon to an Earth-bound observer also varies, as you can see here. And you can see how the perigee looks to you much larger than the apparent view in apogee. Next one, please. So let's now add another variable, or complication if you prefer, to the Earth-Moon system, one that was first derived by Johannes Kepler in the early 17th century. You heard about Johannes Kepler at the beginning of the meeting. Kepler determined that when the Moon is close to perigee, in other words, closest to the Earth, its orbital speed is greater than when it's close to apogee, in other words, when it's further away from the Earth. Interesting, but so what? Why should you care? Next one, please. Well, this phenomenon is what lets you see around the corner and glimpse a small part of the other side of the Moon, the part you're not supposed to see, as illustrated here. Here's how it works. The constant spin or rotational speed of the Moon about its own axis, combined with a faster than average orbital speed when passing perigee, means that the Moon has actually orbited beyond 90 degrees in the time it took it to rotate about its own axis through 90 degrees. That marker there is now rotated 90 degrees. This allows us, if you look at this line of sight here from the Earth, this allows us to see a bit more of the Moon along its trailing edge. That's the trailing edge on this side here because it's going around like this. As the Moon slows its orbital speed, swinging around apogee, the reverse occurs, and we get to see around the leading edge of the Moon. So again, here, that line of sight taking us to here. Technically, this phenomenon is known as the libration of longitude, and you can find predictions of what this means for observing, in other words, for you and your telescope, every month in the main astronomy magazines, or you can check it out on the web. Next one, please, Chris. So if we now put perigee, apogee, and libration together, this is how the Moon would appear to you, speeded up, of course, if you could stare at it without taking a break for a whole month. Notice it's changing in size, apparently. It's rocking left and right, apparently. It's and the migrating terminator and the shadow pattern sweeping across the surface. So this is why one look at the Moon is never enough. It's forever changing in its appearance. Next one, please, Chris. Okay. So now that we've established the fundamental components of the Moon's orbital geometry, let's take a look at some of the consequences, because this is the interesting part. Because the Moon's orbit is oblique by about 5 degrees to the ecliptic plane, it intersects that ecliptic plane at 2 points, technically referred to as nodes. The line linking the two nodes is called the line of nodes, and by definition it lies in the ecliptic plane. So there are the nodes, and there's the line of nodes linking them. Now, this diagram tells us that for most of the time in any given lunar orbital cycle, the Moon is either above or below the line of nodes. So the question from our point of view is this: what happens when the Moon coincides with the line of nodes? And the answer is it all depends on the Sun. Next one, please, Chris. Now, the Sun, by definition, lies in the ecliptic plane. And according to this overly simplified diagram, when the Moon lies along the line of nodes, as here, for example, the Sun and the Earth and the Moon are in line, and lucky observers on Earth get to see an eclipse. Which kind of an eclipse depends on the location of the Moon along the line of nodes. Here we see the Moon located at the node between the Earth and the Sun. Earth, Sun, Moon. Which results in a solar eclipse as the Moon blocks the light of the Sun. Next one, please, Chris. And in contrast, when the Moon is located at the node on the far side of the Earth from the Sun, we get to see a lunar eclipse as the Moon enters the Earth's shadow. Now, this sounds really nice and simple. Why am I standing up here telling you this? Because we have a major problem. These last two diagrams imply that we should be seeing a total solar eclipse every month, followed by a total lunar eclipse 2 weeks later. And this is not what happens. In fact, eclipses were notoriously difficult to predict for pre-scientific societies, as some astrologers found out to the cost of their lives. If we want to understand the role of the Moon in eclipses, we need to introduce 2 more complications to this rather simple story so far. Next one, please, Chris. So here's the first one. So far, we've talked about the long axis of the elliptical orbit of the Moon as though it was fixed in orientation with respect to the stars. And it's not. It would be fortunate if it was, but it's not. It rotates. And it rotates, hit again, Chris. There we go, that's what we're missing. It rotates in the same direction as the moon orbits the Earth, and the Earth spins on its axis and orbits the sun. In other words, in the same direction that most planets and moons orbit and rotate in our solar system. This rotation of the long axis of the lunar orbital plane takes about 9 years to complete. Next one, please. Now here's the second complication. That line of nodes, which is this thing here, there are the two nodes and there's the line joining them. That line of nodes also rotates within the ecliptic plane over a period of approximately 19 years, about twice as long as the rotation of the long axis of the lunar orbital plane. But it rotates in the opposite sense. It's called retrograde rotation. In other words, it rotates backwards. Now, I had to struggle with this concept of backward rotation for quite a while before I finally understood, or at least I think I do. I'll explain in the next slide. But before I do, why is this important? Why do we need to complicate our lives with yet another complication? It's important because the rotation of the line of nodes, that's this thing here. The rotation of the line of nodes within the ecliptic plane really makes a mess of predicting when the line of nodes will point to the sun, and therefore when eclipses can occur. All of which means that predicting when eclipses, lunar or solar, will occur depends on knowing when the moon is located at one node or the other, and when that line of nodes is aligned with the sun. This is not an easy problem to understand, but I'll try and walk you through it as simply as I can. Next one, please, Chris. First, we need to answer the question, how do things rotate both forwards and backwards at the same time? And if we look at a simple orbital ellipse, that's the thing that's marked in the red dotted line here, and its intersection with the ecliptic, which is drawn here as a yellow elliptical thing, then we can define the line of nodes. There we go. The nodes are there, and there's the line of nodes. Next one, please, Chris. If the orbital ellipse now rotates, hit it again, the line of nodes must rotate in the same sense. So we've got a problem. We're missing something here. We know the line of nodes rotates backwards, not forwards. What are we missing? Precession. Essentially, precession is the same wobble you see in a child spinning top, just before it falls over. Next one, please, Chris. Here's a simple Mickey Mouse representation of a spinning disk. The disk is in red, and its spin axis is in white. Think of this as a spinning top. It's going to wobble. If we now represent three positions, different positions of the wobbling top, spinning top, we're going to hit it 7 times, Chris. It's slow succession. Once, twice, 3 times, and again, and again, and again. And there we go. We see that and hit it one more time. There we go. And we now introduce an ecliptic plane in yellow. Something terrible has happened. The line of nodes has not moved. This is because I can't draw. Hit it one more time, Chris. I can't draw, so I've only represented a back and forth rocking of the top. Hit it again. And one more time. There we go. If I could draw for you true precession of the top, the line of nodes would have rotated, either prograde or retrograde, depending on the sense of the wobble. Now, forget the child's top. Imagine now the elliptical orbital plane of the moon with a stake through it at 90 degrees to the plane of the orbital plane. That line, by the way, going through it is called the normal. The orbital plane slowly precesses such that its normal wobbles clockwise, in other words, resulting in a backwards retrograde rotation of the line of nodes. Hit it one more time. While the long axis of the orbital plane itself rotates anti-clockwise, forwards. Hit it one more time. And these rotations happen at different speeds. To put it bluntly, if you watch a spinning top, it spins one way and it wobbles, but it can wobble in the same sense as the spin, or it can wobble in the opposite direction, opposite sense of the spin. And that is what we're looking at. Okay, one more slide there. There we go. So much for theoretical explanations. What does this really mean tangibly for eclipses? Next one, please, Chris. So here's the Earth-Moon system, what it would look like without rotation or precession of the lunar orbit. The yellow circle approximates the ecliptic, and the red circle approximates the orbit of the moon around the Earth. Neither of these things should be circles, but it's easier to draw them as circles. The solid part of the red circle is the lunar orbit above the ecliptic, and the dashed part is the orbit below the ecliptic. So we're illustrating here the tilt. The solid diameter of the circle is the line of nodes pointing at the sun. So an eclipse could occur in this particular configuration depending on where the moon is on its orbital path. Hit it one more time, Chris. So here we see the Earth-Moon system 3 months later. The line of nodes does not point at the sun. There's the line of nodes. This is because I've not let it rotate. So clearly, no eclipses can occur here, wherever the moon happens to be. Hit it one more time. And here again, 6 months later, it's potentially eclipse time again, because the line of nodes is pointing back at the sun, depending, of course, where the moon is on its orbital track. That's what will determine if you really have an eclipse. Hit it one more time. This is way too simple, and it will lead to the wrong prediction. It still leads to the prediction of 6-monthly eclipses. So let's now introduce retrograde clockwise precession of the lunar orbit. Hit it, Chris. All right, so here we go again. At time t1, we're set up here for a potential eclipse because the line of nodes, this thing here, is oriented, it's aligned with the sun. Now, this, of course, all depends on where the moon is as to whether we actually get an eclipse. Hit it one more time. Remember, the line of nodes will rotate clockwise. In other words, retrograde backwards rotation. Next one, please, Chris. So here we are now at time t2. And at time t2, the alignment of the line of nodes is once again pointing at the sun. And this gives us another potential eclipse opportunity, again, depending on where the moon is on its orbital track. However, because of the retrograde clockwise rotation of the line of nodes, it took less than 6 months, for this alignment to reoccur. Hit it one more time, Chris. So let's reinforce this point by observing the next return of the alignment of the line of nodes with the sun at time t3. This is clearly not coincident with the position of the Earth at time t1. In other words, this is not an annual cycle. It's much more difficult to predict. And of course, we still need to know where the moon is as well in order to predict eclipses. Next one, please, Chris. Okay, so perhaps you thought, like I thought at the beginning of this talk, was that the simplest possible astronomical observation was to look up in the sky, night or day, and spot where the moon is. Well, now you know better. Try as I may, I cannot make this stuff any simpler. It's inherently complicated because we're talking about wheels within wheels. Those wheels are not circular. They don't spin at constant speed. Their shapes change orientation, and their axes wobble. And this is just the orbital paths. We're not even talking about the objects that are actually doing the orbiting itself. Now, I don't expect you to have assimilated all that I've talked about here tonight in one shot. And in fact, I bet there are some of you who will go out looking for things to read to get a better handle on all of this. If you do, you are going to come across some unavoidable vocabulary. Just check out the lunar section of the RASC Observer's Handbook, whatever the year. For example, what's the definition of a lunar month? You can't get a simpler question than that. Well, you can. The answer is that depends on your reference frame. Bear with me for 2 more minutes and we'll sort this one out. Let's start with the moon, Luna, that's its official Latin name, sitting there at L1. There's Luna sitting there at L1. And this is the new moon with the moon interposed between the Earth, in green here, and the sun. And that, of course, again, is the representation of the Earth's, the moon's lunar orbit. Seen from above the ecliptic, where you're sitting, the ecliptic is in yellow. The moon orbits the Earth. The moon orbits the Earth. That's the red circle there. In an anti-clockwise direction, in the same sense as the Earth, which is in green, is orbiting the sun. Hit it twice, Chris. A month later, and I say a month in inverted commas, at L2, the moon returns to the same position with respect to the stars. Hit it one more time, Chris. But because the Earth has moved with respect to the sun on its own orbit, We on Earth have to wait for the moon to keep orbiting the Earth a little longer before you actually get to see the next moon, new moon, here at L3. So to summarize this diagram, the time required for the moon to return to the same position with respect to the stars is called a sidereal month, from the Latin for star. And it takes 27.3 days to complete. Remember that number? We'll have a pop quiz at the end. The time between the two new moons, as seen from the Earth, is called a synodic month. And that's from the Greek for meeting or the convergence of paths. And it takes 29.6 days, 2.3 days longer than the sidereal month, in order to compensate for the orbit of the Earth around the Sun. Think of it this way. The sidereal month is a month of absolute rotational positions, while the synodic month is a month of lunar phases relative to us on Earth. Next one, please, Chris. Okay, sidereal, synodic, if I can pronounce them, are commonly used terms when talking about the moon. But the RASC Observer's Handbook also refers, cryptically, each year, to two other lunar cycles, which you may have heard of, anomalistic and draconic. But unfortunately, depending on the year, the RASC Handbook either has no explanation of what they are, or the explanation is extremely dense. Or rather, it's not even dense, it's fleeting is the word I'm looking for. So if you've stuck with me this far, and I hope you have, these monthly cycles are now easy to explain. Believe me, this is going to be real easy. Compare with what I just told you. Hit it one more time, Chris. Okay, let's see how we're doing. Yep. Now, the anomalistic month is simply the sidereal month. Remember, that's with respect to the stars. The sidereal month plus a small correction of 0.2 days to allow for the prograde rotation of the long axis of the elliptic orbit of the moon. Hit it one more time. Okay. And one more time. Oh, no, go back one, Chris. That'll do. I must be missing something there. The draconic month is the sidereal month. That's again, the sidereal month is the month with respect to the stars. Is the sidereal month minus this time an even smaller correction of 0.1 days to allow for the retrograde motion of the line of nodes due to the wobble of the lunar orbit. Next one, please, Chris. Okay, so there you have it. The deceptively simple Earth-Moon system is complicated enough to make my brain hurt. If anyone knows of an easy to read, and I insist, easy to read, well illustrated, I insist, well illustrated, and lucid, please, lucid, explanation of the Earth-Moon system on the web, I would be glad to hear about it. I found several reasonable ones, but none seemed complete. It was bits here and bits there. So enough from me tonight. If you want to run through this stuff at your own pace, I'll be asking our webmaster to post it on the RASC Ottawa website when he can get around to it. After all, remember, we're all volunteers. Meanwhile, I hope you found this a useful summary of the complex behavior of our nearest astronomical neighbor that will help you better understand why the moon is where it is when you're looking up at it. Thanks for listening, and happy year of the solar system. I thought you might.
Yeah. I was thinking about what you said about the wobble, but the Earth also has a wobble that traces a circle somewhere in the North Pacific, I believe. And it's over a very long period of time.
23,000 years.
Correct. Does that have any bearing on it?
No, because the wobbles we're talking about are essentially 9 and, did I say 19 years? It's a very, very different time frame. If you could hang around for, say, 5 to 10,000 years, then yes, if you wanted to compare what you were seeing today with what you'd be seeing in 10,000 years' time, then you'd have to take that into account as well, yes. Meanwhile, while we're just trying to work out why this month the moon seems to be up there, whereas last year it was behind my neighbor's houses at a certain time of the year in a certain phase, this is the explanation. Paul.
Are you aware that the moon is above the horizon more than 12 hours, whereas the stars are only there 12 hours? Since the moon moves eastward among the stars, approximately its own diameter, if you see the moon rising, with a star, let's say under it. By the time they set, the star has already set, but the moon is still up. I think a lot of people aren't aware of that.
I wasn't aware of that. And remember, I put that rider. I know there are people in this room that understand lunar orbital mechanics better than I do. Paul seems to be one of them, and I'm sure there are a few others. I know there's a few PhDs in physics in the room.
With all those complications, how did the ancients manage to predict the eclipses so well?
Well, as you know, they commonly didn't. And in certain cultures, the chief astrologer would literally lose his head. And this was one of the most difficult things in astrology to actually predict.
Thanks, Simon. That was wonderful. Thank you. Okay, I'm going to motor through the last of these because we are running a bit late, and I know some people want to get to the after-meeting and wet their dry throats. Just wanted to let you know of this. There's actually a blog contest from the RASC that's open now. I'm not going to read through all that because it's fairly lengthy, but if anybody's interested, please come and see Chris or myself after the meeting there, and we can throw the slide up on the computer for you there. But it is an interesting little contest, and apparently there are prizes involved. So for those of you that are interested in blogging, you may want to come up and talk to us afterwards. All right, Estelle, yes, Estelle is here. We have Estelle's pick of the month is Deep Sky Wonders, and apparently that is quite a book. And the library will be open, Estelle?
Give me 2 minutes.
All right, 2 minutes it is. Okay, post-meeting entertainment. Yes, Al Scott, who is in Florida today, won't be with us, so he's down there complaining about how cold it is. And I really feel for him, you know? Yeah. Coffee and conversation out in the lobby with Arden Ann Fraser. Again, if for those members that are, or visitors that are new that haven't joined yet and aren't scared away by today's session there, please see Art Fraser for membership information. He also has membership cards for those that don't yet have them. Sky and Tel and Astronomy Magazine renewals, Stephen McIntyre. And just to remind you again, the rest of the museum is closed. If you hear strange little people sounds out there, there is a sleepover going on there, so don't go there. Don't go there. And again, I guess reservations have been made? Have we not? No?
They're always made.
They're always, oh, they're permanently made. Okay, again, newbie, right? So snacks and drinks or dinner at Kelsey's across the way there. And tonight we had 113 folks in the audience. That's great. And I want to thank the organizers, Chris and Bill, Sylvie, Pierre, Paul, Gordon Webster, and Simon. And thanks for our host, the Canadian Museum of Science and Technology. And a special thanks to our navigator of the starship, RASC Ottawa, Chris, for his usual excellent work and helping me to pull things off and not totally botch it tonight. So thank you very much. Next meeting, February the 3rd. Hope to see you there. Good evening.